All right, we got 6 people here. There should be more people. I'm happy to see you though. Ashley, Jacob, Tabor, Will, and Will. Oh, here comes Zane. All right, let me share this. All right. Hi, good to see you. How's everybody doing? Oh, there's a smile from Jules. That's nice. Anybody else having a good day? There's Tabor. Hi. All right, let me put the chat up. In my first class of the day, Siri thought I said something about, I thought I said something about like going to find the devil bar, or I don't know why, what I said that sounded like that, but it started saying, you know, I don't know where that is, I'll search for it. And oh God. So yeah, I'm worried now because I know in this class I'm going to say series and it's gonna like just be all over the place. All right, so how's it going? Anyone have anything fun happen this week?
I went surfing before class. My hair's still wet.
Oh, yay, yeah, all right. I haven't really, you know, I used to get a lot of exercise and lately I just haven't, and I'm really feeling it. So Zane's doing it for us. That's awesome. Plus surfing's just fun. I'm a horrible surfer. I have a surfboard and you can't call me a surfer. Like I sometimes go out to try to surf, but that's not the same thing as being a surfer, right? It's just to flail around and, but yeah, it's fun. Right, anyone else do anything fun? All right, well, I'm gonna do that surprise this weekend. I think I told you. So I hope it turns out and I'll have something weird to show you on Tuesday. That will be both embarrassing and cool. All right, but you know, in the meantime, let's talk about, what is it, 8.5 that we're on now, section 8.5. Power series. All right, this is where we're all building up to. Well, Taylor series are where we're all building up to. Taylor series are a special way to find power series. In fact, they're a special way to find power series and connect them to other functions. And that's really the ultimate goal. But power series, you know, we've come so far. Like, so what have we done? We understood what a sequence was, just a list of numbers, infinitely many. And then the series, we're going to add up infinitely many numbers. Sometimes that doesn't get to, sometimes that's infinite. You know, we should be surprised that it's ever a finite number, but in fact, it is a finite number lots of times, and we've been finding different ways to show that series converge. Those are individual series. A power series involves variables, and so for a variable x, and for some values of x, you get a regular series that converges, and for some values of x, you get a regular series that doesn't converge. And so we're trying to find out for these power series, for which x does it converge and which x doesn't it converge. So I'm going to start us off. We did 4 examples already, and so I think we're like in a good place to try something on your own. So let's try it with the classwork. So let's think about this series, n equals 1 to infinity, 0 to infinity, sorry, because we're a power series. X minus 2 to the 2n plus 1 power divided by natural log of n. Perfectly good series. And so my question is, find the interval of convergence. Does that make sense? Yeah. What's our main tool going to be? Can somebody remind me?
Ratio test?
Yeah, ratio test, absolutely. All right, so get on that with the ratio test. So I'm going to put you into breakout rooms, give you like 10 or 15 minutes. You may or may not have a chance to finish it, but then we'll come back and talk about it. And then move on. So 6, create, open. Hi, we're in breakout rooms now.
Oh, hi. Okay.
Hi, working on a classwork problem.
Okay.
Hey, Will, where are all your friends?
What's going on? No idea. I'm sorry. I'm eating.
Don't be sorry. No, I don't blame you. You need to keep your strength up. Is it okay? Can I put you in a room where there's more people so you can have something to talk, someone to talk to?
You could do that, or you could leave me here. I was personally watching videos on other ways to approach this. So
Okay.
that's what I was currently doing.
Okay. The only way to do it is the ratio test.
Yeah, so I was watching, like, understanding the ratio test better, me personally.
Okay. Okay.
If that's okay.
So if you want to move to a different room, you're allowed.
Okay, thank you so much.
Sure, I'll see you. Let me check this guy out. Garrett. This
Professor, how are you?
is a group right here.
What's that?
This is a lonely group right here.
Yes, it is.
You want to put in with another group?
No, that sounds good.
Okay, let's see. So these people are pretty talkative. Which do you like, talkative or not talkative?
We can do talkative. Why not?
Okay, I think let's try, yeah, these people like to be quiet, but these people like to be talkative. Let me put you in with this group here. Hey everyone, I just dropped Garrett into your group because he was in a group of one, and that's not a very good group. So I told him that you were all talkative and friendly, although now you're being very quiet. But sometimes you're talkative and you're always friendly. Does anyone have a question? Not
So
yet?
far, so good. Yeah.
So far, so good. All right, I'll check on another group. Hey, just stopping by to see if there's any questions.
Doing good.
Okay, all right, Jacob, you too?
Yep.
All right, let me check another group. Hey, just stepping in. Are there any questions?
Could you multiply by e to drop off the ln's to get n over n plus 1?
No. So one thing is that it wouldn't be multiplying, it would be taking it to a power. You know, so
What was that you cut out?
it wouldn't be multiplying. You would be taking e to the power of ln, but you can't do that either because, you know, because a number is different from e to that number. So you just be changing the problem.
Okay.
But you can, you could use L'Hopital's rule.
Oh, thank you.
Yeah,
That's what it is.
that's what you need. Right. Let me check in this other group. Just thought I'd stop in. Does anyone have any questions they want to ask?
No, none right now. Just getting through the ratio test. So right now, just discussing what is happening in that process.
Okay. All right. Well, I'll leave you to it.
Thank you.
So yeah, I think that works.
And I got to 1 too when I did that.
So now questions, or are you happier when I'm not here?
I think we're good right now.
How close are you to
Yeah.
done?
Pretty much done.
Pretty much done? All right. Okay, maybe it's time to call everybody back. Hey, Kishan.
Hello.
Everybody was in breakout rooms, but I'm just calling them back now.
Oh, okay, perfect. I'll just stay here.
Get everything open back up again. All right, so it sounds like some progress was made. How many groups figured out where it converged, but we're still working on the endpoints? Did that happen? Yeah. Does anybody want me to show the entire problem? Yeah, okay, all right. So first we're going to use the ratio test. And that's just going to be, we want the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. A sub n plus 1 is, so we've got x minus 2 to the 2n plus 1 over ln of n plus 1. And then we're going to multiply by the reciprocal like we've been doing. So that's going to be ln of n over x minus 2 to the 2n plus 1. All right, and that cancels. Let's sort this out a little bit. So this is going to be x minus 2 to the 2n plus 2 plus 1, so 2n plus 3. All right, so a lot of these are going to cancel. 2n plus 1 of these are going to cancel, and then I'm just going to get a squared left. I can pull that out in the front like we've been doing. So I'm going to have the absolute value of x minus 2 squared. I don't even need the absolute value since it's squared, but I'll have it for now. Why not? So absolute value x minus 2 squared times limit as n goes to infinity of ln of n over ln of n plus 1. Do I need those absolute values? When is natural log negative? Is it ever negative? Sometimes it is. It's negative up until ln of v is 0. In fact, I can't even write this. I have to start at 1 because ln of 0 is undefined. ln of 1 is 0, so we should really start this at 2. Everything else works the same way. I just don't want to have bad math involved. All right, well, sometimes ln of n is negative, but as n goes to infinity, then it's positive from then on. So let's just go ahead and go with it. What happens to ln n as n goes to infinity? Where does that go?
Infinity.
Infinity, that's right. So the numerator goes to infinity, and then the denominator also goes to infinity. So that's infinity over infinity in determinate form. We can't do our cute stunt of like dividing top and bottom by the highest power of n. These aren't powers of n. But we can use L'Hopital's rule. What about like L'Hopital's rule? Let's try that. So, oops. So we still have this constant in the front. So L'Hopital's rule, you don't take the derivative of it as if it's a quotient. You take the derivative the way you wish the quotient rule worked. You just take the derivative of the top, you just take the derivative of the bottom, and you put them together. So this is going to be 1 over n on the top, and then 1 over n plus 1 on the bottom. And then doing some algebra. Oops. I multiplied, well, it's really, we're going to multiply by the reciprocal. So it'd be 1 over n times n plus 1 over 1. So n plus 1 over n. Now we can do that step. Multiply top and bottom by 1 over n. And we're going to get 1 plus 1 over n over 1. And when we take that limit, that thing just goes to 1. In fact, don't need absolute values. Because x minus 2 squared is always bigger than equal to 0. Okay, so this is our limit. Did anybody get that far? Okay, a couple of nods. Okay, nice. Okay, so does anyone want to ask a question about this before we go forward? Okay, this is our limit. And when it converges when that limit's by the ratio test, it converges when that limit's less than 1. When's x minus 2 squared less than 1? Think about the squared function. Here's f of x equals x squared. Where's the squared function less than 1? The answer is it's when the input's between 1 and negative 1. Oops, I made a bunch of mistakes here. Does that make sense? Does that match your mind of how the squared function works? So that means this happens when x minus 2 is between 1 and negative 1. So this happens when add 2 to all pieces, 1 less than x less than 3. So, so far, we can say the interval of convergence is, well, it's between 1 and 3, but we don't know whether we get round brackets, square brackets. We don't know what we have. So right now, I'm just going to put a little question mark on either side, right? I don't know whether it's round or square, whatever, but it's the interval between 1 and 3, possibly including some of the endpoints. What do I have to do next?
We
Test
gotta,
for convergence at the endpoints.
Yeah, we're gonna have to check the endpoints. See whether it converges at the endpoint. So let's try those bits. So the endpoints, x equals 1 is one of them. So check the endpoints. Right. Let's go back all the way to our, here's our series. don't want to forget anything. Let's put this as a 2. All right, I'm gonna have to plug in x equals 1. So this is going to be, oops, 1 minus 2 to the 2n plus 1 power over ln of n. Negative 1 to the 2n plus 1 power over ln of n. What kind of series is that?
Alternating?
I was hoping somebody would say that. So that's kind of it was kind of a trick question. It looks like an alternating series, doesn't it? It's got the negative 1 to some power. If we do a little bit more algebra, maybe we can really see what's going on. See, 2n plus 1, no matter what n you give it, that's always odd. You give it an n multiplied by 2, that's always going to be even. And then you add 1 to it, that's always going to be odd. So it's always going to be negative 1 to an odd power. So it's not even going to alternate, it's just going to be negative all the time. And another way to see that, if you want to see it with the algebra, I can write that as negative 1 to the 2n times negative 1 to the 1 power. But negative 1 squared is plain old 1. Ugh. This is nothing, right? This is not positive, so we can't use the integral test or the, let me turn that off. We can't use the integral test and we can't use the comparison test. We can't use the limit comparison test. It's not alternating. We can't use the alternating series test. I guess we could use the ratio test, but wait a minute. This is the thing that made the ratio test equal to 1. So this isn't going to tell us anything. Here's what we can do. This is a little bit of a roundabout thing. I'll just be honest, but I'm not going to focus on it because I think focusing on it will confuse you more than I need to. But if it converges, we can factor the 1 out, the negative 1 out. If it doesn't converge, then we don't care. It just diverges. Okay, so this is true if it converges. And if it diverges, then the negative diverges too. Okay. The point is, if I have a bunch of positive numbers and I add them together, and that sum ends up being a finite number like 27. What if I then take every single one of those numbers and multiply it by negative 1? That sum's going to be negative 27, right? We just multiply each of the terms by negative. We can factor the negative out of all of them. Okay, so if the positive part, if this thing converges, then the thing with the negative side is also going to converge. So we're just going to analyze for convergence. Well, it's not quite all positive because ln2, ln2 is 0.69, ln2 is positive. Okay, so, oh wait, stop, undo. ln2 is positive, so that's pretty cool. So it's all positive from here. These are a series of all positive terms. So what test do you want to use? We can use anything from 8.3. Well, do you know how to integrate that thing? I don't. Plus the integral test kind of sucks. What about, let's use a comparison test. So use, I like the limit comparison test. So use limit comparison test to compare with, what's a similar series? Nothing really. But we've only got geometric series and P series. So what's a good thing to try?
Maybe root n.
Maybe root n. Oh, that's clever. Yeah, because if you think about ln n, right, it's kind of like that. And root n is kind of like that. So maybe those seem like good things to compare. Yeah, that's clever. I was just going to do 1 over n, but root n actually looks more like it. What do I need? What are the conditions for a limit comparison test?
Positive and
Yeah.
something you know.
Yeah, and something you know, that's right. So they better both be positive. So let's see. ln n is bigger than 0 whenever n is bigger than 1. So it's positive from 2 on. That's fine. And then what about 1 over the square root of n? This is always positive. We're taking the positive square root. Okay, so those are really the conditions if they're both positive. And then we have something that we know about. We know about 1 over root n. So let's just use the limit comparison test. So we're going to take, so now take the limit. Okay, so for limit comparison test, we take the limit n goes to infinity. We put the thing that we don't know about on the top and the thing that we do know about on the bottom. And take the limit. So again, I'm going to multiply by the reciprocal. So I'm going to get n to the 1/2 power on the top and ln of n on the bottom. You see how I did that? Maybe I need an extra step. This would be 1 over ln n times root n over 1. Numerator and denominator still go to infinity. So let's use L'Hopital's rule again. So what do I have? I have 1/2 n to the minus 1/2 times n. These will cancel. So I have 1/2 square root of n. And as n goes to infinity, this diverges. Oh, wait, sorry. I didn't mean to say that. If it goes to infinity, then what has to be 2? What does the limit comparison test say?
Then the other one also diverges.
That's right. That's right. So since we took the limit, now as a result, we know that the first one, or we know that the one we came up with diverges because it's a P series with P equal to 1/2. And most importantly, that's less than or equal to 1. So by the limit comparison test, this guy also diverges. Is that true? Yeah, suddenly I'm feeling like that might not be true.
If it's less than it, it'd be true.
Yeah, that's the regular old comparison test. What is it? Feel a little concerned about this, so I'm looking up the. That's plain old comparison. Hold on, let me find it. Oh, they don't have a general one. Can anybody look back in their notes and see if that's really true or not? Maybe I can do it. So what did the
It
limit?
says if the limit of a n n over b n n is equal to infinity and b of n diverges, then a of n diverges.
Oh, okay, good, awesome. Thank you so much. Where was I? Here. Okay, so by the limit comparison test, this other series, 1 over ln n diverges. And therefore, negative 1 over ln n must also diverge. All right, so this guy, nope. Where is he? X equals 1, nope. There's another endpoint. It won't be as bad, don't worry. The other endpoint is x equals 3. Let me pick up our series again. Oops. If I plug 3 into it, well, this is just 1 over ln n, but we just did that. So diverges by the work we did above. So not there either. So in conclusion, the series converges in the interval between 1 and 3 and not including the endpoints. All right, let me just pause and see if anybody has anything they want to ask about that. So there's a lot of steps. It's kind of long, right? I mean, we started here, took us all the way to here. 2 pages worth, is that right? 3 pages worth? Okay. That doesn't mean we can't do it. That just means that, you know, we have to be patient. We just have to settle in. We'll get there in the end. We know how to do all the pieces. We just have to build our stamina so we can get through to the end. All right, before we leave this section, I'm just going to give you a couple of facts that you can use that may be helpful on homework problems or in the fun pack or something like that. So here's fact A. Limit n goes to infinity, n factorial over n to the n is 0. And here's another fact. Limit as n goes to infinity of x to the n over n factorial was also 0 for every x. So we don't know that's a number. This may seem weird. It may seem like I took the reciprocal and I'm claiming it also is 0, and that shouldn't make sense, right? It should be that if I take the limit of something and it's 0, then when I take the reciprocal, it ought to go to infinity. But it's not exactly the reciprocal, because this thing isn't increasing when n increases. This is just a constant as n is increasing. And so that limit's 0. And you may, when you use them, when you get to a homework problem or a fun problem, you can just say by fact A. All right.
Can we use this fact on test?
You can, yeah, if you remember it correctly. And in fact, maybe you won't even know whether it's fact A or fact B, but if you say by fact A or B, like you don't remember, that's fine. I'll know which ones you're thinking of, and you can use it on the test too, actually. Yeah, good question. And test. All right, any other questions? All right, inching our way forward. Section 8.6, this is the reason why we're doing this. Representing functions as power series. This is the reason why we're learning power series. This is the reason why we learn series. Let me just remind you, functions are very complicated. And, you know, we have these fancy calculators. A calculator doesn't really know what ln is. It doesn't know what sine and cosine are. It knows how to add, subtract, multiply, and divide, take powers. It knows polynomials. That's what it knows. It doesn't know all this other crap. So instead, it just thinks of the other functions as polynomials. Well, they're not. They're infinite polynomials. But if it converges, it doesn't matter. Like you can get as close as you want to the answer by taking enough terms. So maybe you have to take 450 terms of the polynomial, but your calculator doesn't care. It'll just do it. And you might have always thought that the number that you get out of your calculator is exact. It's 100% perfect, exactly right on. That's why you use a calculator, you always get it right. But in fact, it is not exact. It's only exact up to the digits you can see. And maybe your calculator shows you 10 digits. All those digits are correct. But maybe when it did its math, you know, all the rest of the digits would have been garbage, but it doesn't care because you won't see those digits. So that's why it's okay for calculators to give you estimates. As long as it gives you an estimate that's accurate to 10 decimal places, you don't care if the 11th decimal place is wrong in its estimate. So power series, this is a way to treat functions like polynomials. And so we're gonna, and so that's what it means to represent a function as a power series. Find a power series that gives the same values that the function gives. And there's so many uses, and I hope we get to some of the uses. All right, but we'll see how time goes. So there's going to be this section. We're gonna exploit an example we've already talked about as much as we possibly can to get power series for a bunch of functions. And then, we're going to get stuck. And then we're going to say, well, what are we going to do in general? This only works for these sort of weird category of functions. And then section 8.7, that's going to be what we can do in general. Okay, but for this section, I just want you to sort of recall a key example. I keep bringing this example up. I brought it up a couple of times because it's important. So I'll do it again. This sort of most simple power series. So this power series one plus x squared plus x cubed plus x to the fourth plus going on forever. So in other words, it's the sum of all the x to the n powers. It's a geometric series. With a is equal to 1 and r is equal to x. It converges when does it converge?
When the absolute value of r is less than 1.
Yeah, when the absolute value of r is less than 1. So it converges when absolute x is less than 1. And when it converges, what's the sum? Remember, it was a over 1 minus r. That was the sum for a geometric series. A is 1 minus x. All right, here's our example then. This function, 1 over 1 minus x, can be represented by this polynomial. By this power series. As long as x is between -1 and 1. Geometric series gave this to us. And this is we're going to lean very heavily on this fact for every single problem in the rest of the section. So, so do something in your notes that really calls good attention to it. Okay, let's think of some examples. So does everybody remember this example, or do you want to ask a question before we move on? Since the rest of the section is based on it, if there's something you don't understand here, it could cause problems later on. So I'm happy to get that cleared up if there's anything somebody wants to ask. All right, let's try some examples. Here's one. So all these examples are going to be the same thing. Express the following as a power series and find the interval of convergence. Oops. How about this one? F of x equals 1 over 1 minus x squared. Well, that's pretty close to this, right? The only difference is there's an x here instead of an x squared. So if I plug in an x squared for here, that's the same as plugging in an x squared for here. So using the key fact, this is going to be does that make sense? I just plugged it in. I know that these functions are equal. So if I plug in an x squared on the left side, it's the same as plugging in an x squared on the right side. So all this is true. I'm going to say it's by the key fact. This is key fact. Where did it go? And that's just, you know, x to the 2n power. So if you want to just feel more comfortable with it, that's x to the 0, which is 1, plus if n's 1, that's x squared. If n's 2, that's x to the 4th. Okay, is that polynomial? How do I know where it converges? You may be tempted to use the ratio test. Sure, that'll work. But we can do even better because of the key fact. The key fact, I probably should have written it. I mean, this is true, but let's just write an absolute value. It converges when absolute value of x is less than 1. It converges when the thing we stuck in is less than 1. So it converges when when's the absolute value of x squared less than 1?
When x is less than 1.
Almost. If I put when x is less than 1, so what if x is negative 10? Negative 10 is less than 1, but when we split
The
it.
absolute value of x is less than
Yeah,
1.
there you go. That's right. Absolute value of x is less than 1. So it converges in the same place between -1 and 1. If I wrote interval of convergence, I could have wrote the interval is the interval between -1 and 1, but we don't include the endpoints of the interval. All right, let's try another one. F of x equals x minus 2. Sorry, 1 over x minus 2. It's not the same, right? This is 1 over 1 minus something. It's not 1 over 2 minus something. It's not 1 over something minus 2. We have to get it in that form. We have to be pretty careful. So let's try to do this algebra. So I really want the x, I really want it to be number minus x instead of x minus number. So I can multiply top and bottom by a -1. Let me pull that negative sign out a little bit more, actually. But it's still not what I want. I want 1 minus x, and I've got 2 minus x. That's not cool. So I can factor a 2 out of the bottom. And that's okay. So let's factor a -1/2 out here. Then I've got 1 over 1 minus x over 2. Now, this thing right here is in the same form as the key fact, 1 over 1 minus thing. Here's the thing. So this is, you know, I got the -1/2 in the front. Sum n equals 0 to infinity. That thing to the nth power. gonna do some more algebra because that doesn't look like a power series. A power series has to have number times variable to the n. So this is gonna be negative a half. I'm gonna have 1/2 to the n times x to the n, full number away from the variable. Oh, there's another 1/2. I can multiply that 1/2 in. I can multiply that negative 1/2 in. So I've got n plus one more of them. So I've got it in power series form, number times x to a power. And it converges. Oh, yeah, that's right, it converges. When this thing right here, the thing that took place of the x is less than 1. In other words, that's when -1 is less than x over 2 less than 1. Or, yeah, I'm trying to integral converge, that's fine. And I multiply everybody by 2.
Yeah, you just throw it in. The top front doesn't matter unless you want to rinse it off. Either.
Was that too easy?
Dealer's choice.
Thank you, Stan, my friend. Okay, so that means the interval of convergence.
My bad.
No problem. It's nice to hear a voice. Everything from -2 to 2, not including the endpoints. Do we need another example? Let's do another one. Let's get a little bit weirder. How about f of x equals x over 9 plus x squared? Remember, the thing that we're trying to hit is 1 over 1 minus x. That's where we're heading for. I don't like that x on the top. So I'm going to factor that out. That's better. I've got a 1 in the numerator. That's what I want. But I also don't like that 9 either. So I'm going to factor the 9 out of the denominator. Let's pull that all the way out. So that's going to be x over 9 times 1 over 1 plus x squared over 9. That's a lot closer. What's missing? Or what's different?
You're adding the thing we're trying to find.
Yeah, I'm adding and I need to be subtracting. That's okay. Addition is just subtracting a negative. So here it is. Negative x squared over 9. That's the thing that takes the place of x. So by the key fact, this is x over 9 times this sum and equals 0 to infinity, that thing to the nth power. I'm going to do some algebra and tidying things up. Okay, so I've got, see, negative x to the 2n, negative x squared is kind of like -1 to the n times x squared to the n. Let me put it out that way. Over 9 to the n. So at -1 to the n. Then I have x to the 2n, but if I pull in the other x, I've got x to the 2n plus 1 power. And the bottom is 9 to the n plus 1. And if I want to write it as a power series, I'm going to put the coefficient first, sorry. So I've got -1 to the n over 9 to the n plus 1 times x to the 2n plus 1. I've written it as a power series. And it converges when that thing that we plugged in, what was it? -x² over 9, absolute value, is less than 1. Okay, so that's when, what's a good way to do that? That's when, so, you know, absolute value of x², of -x², the negative goes away. So I'm going to have x². 9 doesn't need an absolute value. Neither does x², in fact. When's x² less than 9? Is it x less than 3? It's not. What's missing?
Plus or minus 3?
Kind of. You can't be less than plus or minus 3, but plus or minus 3 has to come into it. So it has to be bigger than -3 and smaller than +3. Yeah. Okay, so the interval of convergence is from -3 to 3, and we don't include the endpoints. You know, it all comes down to algebra. So much comes down to algebra. And you know, you may have felt the sigh of relief when you left algebra back in high school, or wherever you did, and now you're like, oh boy. It's always coming back. All right. So what time is it? Okay, I have time to tell you something else you can do with this. Here's a little theorem. So you can differentiate and integrate a power series term by term on the interval of convergence. You'll see why that's cool in a minute, but I have to put a little caveat warning. What's the warning being orange? When you do, the radius of convergence stays the same. But the interval of convergence might change. How's that possible? Where would that change have to occur?
on the endpoints?
Yeah, that's what I think on the endpoint. So you might lose or gain convergence at an endpoint, but everything else will converge everywhere that the original thing did. Let's show how we can use that in some examples. How about this one? F of x equals 1 over 1 minus x squared. If I square that out, I'm going to get 1 minus 2x plus x squared. And that's not at all like the thing that I want. That's not at all like this sort of, where is it? Where'd it go? That's not at all like this sort of key fact, this our favorite rational function that we're trying to deal with. Not good. What is the relationship? Can anybody see a relationship between that and the Holy Grail, which is this thing?
Can you pull the square out, like put it all under a square?
Oh, yeah. you
Since
can.
1 squared is just 1.
Yep. And that seems like, and that's actually a really good idea up to a point. So that's great. And I can do, I can go straight from there to, oh, sorry, squared. I can go straight from there to that's the sum n equals 0 to infinity of x to the n squared. Going from here is really, really, really hard. If I want to make that a power series, what does that look like? It looks like, you know, I've got 1 plus x squared plus x cubed plus x to the 4th plus times 1 plus x cubed, or x squared plus x cubed plus x to the 4th. I have a giant infinite FOIL. It's not going to be as nice as we wish it was. Do you know what I mean? It's going to be, I've got 1, and then I'm going to get an x one way and x another way, and then I'm going to get a bunch of different ways to get an x squared, a bunch of different ways to get an x cubed. So this giant FOIL so we're kind of stuck from here. So that was a really great idea that Zane had, but then it turns out like we couldn't get further couldn't get further to finally get a power series. So can't go further. Okay, so let's try it again. So I still have f of x equals 1 over 1 minus x squared. And I've got in my mind, I've got 1 over 1 minus x in my mind. Oops. What if I take the antiderivative? Look how this question was already, this theorem was already about derivatives and integrals. What if we do that? So the antiderivative of f, this is going to be, oops, yikes. This is going to be 1 minus x to the minus 2 power. So the integral of f of x is the integral of 1 minus x to the minus 2 power. And you could use u substitution if you want. But you get -1 over -1 times 1 minus x to the -1 power. So you get -1 over 1 minus x Hey, there it is. So that's negative sum n equals 0 to infinity of x to the n by the key fact. And by the way, it converges when absolute x is less than 1. But that's not what f is. That's what the integral of f is. How do I get f? Oops. I have to take the derivative of both sides to recover f. Right? Differentiation undoes integration. You have to be a little bit careful here when we take this derivative. The problem is, if I just take the derivative here, it's going to look like I've got x to the n minus 1 power. And if I plug in x equals 0, I've got x to the minus 1 power. So I've got 1 over x. That's not a polynomial. Something's whack. I shouldn't be able to take the derivative of a polynomial and get something that's not a polynomial. So I'm just going to write out some terms just to make sure things aren't too crazy. So this is the derivative of, let's pull that negative sign out in front. Who needs it? This is 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th, etc. And I want to take the derivative of that. Derivative of 1 is 0, derivative of x is 1, derivative of x squared is 2x, 3x squared plus 4x cubed plus 5x to the 4th plus. Does that make sense? Derivative term by term. So this thing is f of x. So that means f of x is this thing. So it's going to be negative 1 plus 2x plus 3x squared plus 4x cubed. And we have to figure out how to put that in summation notation. Here's when n is 0, n is 1, n is 2, n is 3. So n equals 0 to infinity. I've still got this x to the n power. That works, right? When n is 0, I've got an x to the 0 here. When n is 1, I've got x to the 1, x squared, x cubed. But what am I going to put for the coefficient? What is the coefficient? How is that related to n?
N plus 1?
N plus 1, absolutely. There it is. There's our power series. And our original function was 1 over 1 minus x, whole thing squared. So there's the power series. And we know that it converges wherever the previous thing converges, except maybe not at the endpoint. So between -1 and 1, but we don't know about the endpoints. So you have to check them. And how would you do that? Well, that's what 8.3 and 8.4 and we're all about, right? Is how do you check when you put constants in? In fact, it looks like if I put 1 in, looks like I've got the sum of n plus 1 and it diverges by the divergence. It looks like it's going to diverge on both of them, but you can check. Okay, we'll do some more examples next time of this very thing. But for now, do homework for 8.5 due Monday. And homework for 8.6, we're not quite done, but we're close enough to done. We could probably have that due, oh, wait, Monday doesn't make sense. Sorry, Tuesday. You could probably have that due Wednesday. Is it easier for you if, yeah, let's just have it due Wednesday, and then maybe I'll push the other one up. Maybe we'll only have Tuesday, Wednesday, and then push it through. So was there anything else due Tuesdays? Is it we've done all the 8.4, is that right? All right, cool. Good to see you. Thanks for coming back. I'll see you. Have a great weekend. I'll see you next week.
Thank
Thank you.
you.
Thank you, Professor.
Thank you.
Bye.